In this video, we're going to look at quadratic sequences. So far, you'll have met linear sequences or nth term problems. Examples might be 2n plus 1 or minus 3n plus 5. In this video, we're going to look at sequences in the form an squared plus bn plus c. These are what we call quadratic sequences. So let's look at a sequence that you might have met before. So we might have some numbers, for example, now 4, 7, 10, then we'd have 13, we'd have now 16, and we'd be asked to find the nth term of this sequence. So if we consider putting this in a table, what we'd have now is n, and we'd have 1, 2, 3, 4, 5. That's the number in the sequence, and the corresponding terms are going to be 4, 7, 10, 13, and then 16. We can see the common difference here, which is the first common difference, is going to be now 3 each time. I'm adding 3. A common mistake is for students to say that this sequence now is n plus 3. Quite clearly it isn't, because if we take n to be 2, 2 plus 3 is not 7. We can see that the first difference is going to be 3. So what we say is the first difference is equal to 3. What we do is multiply now this 3 by the n. So if I do now 3 lots of 1, that's going to give me 3. I now say to myself, what do I need to add or subtract to get to 4? And the answer is 1. Therefore, my linear sequence is 3n plus 1. Does that work for the next one? Well, 3 times 2 is 6, plus 1 is 7. 3 times 3 is 9, plus 1 is 10. This is now a linear sequence or nth term. What we've got here now is n to the first power. If we've got a quadratic sequence, we will have an n squared term in there. If you need to review this, please check out my website, as there's a long list of different problems involving linear nth term. You're going to need to understand how this works, as we're going to now put together a quadratic sequence as a quadratic part and a linear part. So if you want to do some revision, hit pause, go and look at the videos, and then come back to this one. One thing you may be asked to do in an exam is to generate the first 5 or so terms of a quadratic sequence. So let's have a look at a typical example. We're asked to find the first 5 terms in the sequence n squared plus 2. So let's consider now n is 1, 2, 3, 4 and 5. So what we're going to have then is the first part. We're going to have n squared, and then I'm going to add 2. And that will now give me a term in the sequence. So if you're asked to generate the first 5 terms of a sequence or write them down, we can go ahead and do this. So if n is 1, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. Now we're just going to add 2 to each part, like so, and then we can sum these. So 1 plus 2 is going to be equal to 3. Then we got 4 plus 2, which is 6. We got 9 plus now 2, which is 11. 16 plus 2, which is 18. And then now we've got 25 plus 2, which is 27. So we can say now that the first 5 terms of this quadratic sequence are 3, 6, 11, 18, and 27. So that's a case where we generate a sequence now given this quadratic expression. It's quadratic as we have now an n squared term. Linear, we would just have n, or 3n, 5n, and then some other value. It's quadratic because we've got the n squared. So let's look at generating another one. We're asked to find the first 5 terms in the sequence n squared plus 4n plus 1. So if we have n, we can have 1, 2, 3, 4, and 5. So what we're going to have then is n squared. We're going to have now 4n, which we're going to add, and then we're going to have plus 1. So all we're going to do is add these on, so plus 1. So we're going to have 1, we're going to have 4, we're going to have 9, we're going to have 16, and we're going to have 25. We're going to have now plus 4n. Well, that's going to give me now 4 lots of 1. So I'm going to add 4, I'm going to add 8, I'm going to add 12, I'm going to add 16, and I'm going to add 20. I now add 1. If this was minus 1, we would subtract it away. So I'm just going to add 1. What you can see now is that this is going to give us a quadratic part and a linear part. This here is the quadratic part, and this is the linear part. When we're dealing with these quadratic sequences, we're going to have a quadratic part and a constant, which might be 1, minus 2, minus 4, 5, or now this linear sequence. The linear sequence is 4n plus 1. I'm going to use this information later in the video to see how we can work out the nth term given the sequence. So let's look at the sequences and the terms in them. So 1 plus 4 plus 1 is going to give me 6. That will give me 13. This one is going to give me 22. This one is going to give me now 33. And then finally, we're going to end up now with 46. If we now consider this sequence right here, I'm just going to write this out. Writing this out, we've got now 6, 13, 22, 33, and 46. Now, with a linear sequence, the first difference is a fixed value. So we saw last time it went up by 3 each time. If we consider this one, the first difference is not fixed. If we just look across, what we're going to have then, this goes up by 7, it goes up by 9, it goes up by 11, and it goes up by 13. The first difference here is not now a fixed number. If we consider the second difference though, this is now going up by 2, it's going up by 2, it's going up by 2, and it will go up by 2. This now is a feature of a quadratic sequence. The second difference is a constant term. So in this case, the second difference is going to be 2. So we can see now with a linear sequence, the first difference is going to be a constant term, the second difference for a quadratic. We're now going to consider this second difference. If we now see this is 2, this gives us now a term of n squared in our sequence. So if the second difference is 2, and I'll write this here, what we'll have, and I'll just write it out here, the term, if we have n squared, the second difference, and I'll write it here, second diff is going to be 2. If we have now 4, that's going to give me 2n squared. If we have now 6, that's going to be 3n squared. If we have 8, that's going to be equal to 4n squared. If we have 1, that's going to give me 1/2 n squared. And as a generalisation, we can simply say now this is half of the value. So if my common difference here being 8, we would now have a term of 4n squared in our sequence. What we're going to look at doing now is looking through a quadratic sequence and finding the nth term. We're going to consider two parts. We're going to consider the quadratic part and then either the constant or the linear sequence. So let's go ahead and look at one. What we've got here is it says find the nth term for the following sequence. We've got 4, we've got 13, 28, 49 and 76. So what I'm going to do here is the following. I'm going to write in here n. So what we've got then is n, 1, 2, 3, 4, 5. So if I now consider the term, I've got 4, 13, 28, I've got 49, and I've got 76. So let's look at the first common difference here. The first common difference in each term we're going to write down. So this is going up by 9, this is going up by 15, this is going up by 21, and then this is going up by 27. That is the first difference. Let's now look at the second difference. The second difference, that one goes up by 6, this one goes up by 6, and this one goes up by 6. Therefore, we can say that we're going to have now a term of 3n squared in now my quadratic sequence. And I'm going to write this here. Now, if we have 3n squared, I'm going to work out those values. So let's just put these in. Now, what we do with 3n squared, we take n, we square it, and we times it by 3. Don't get caught into the trap of doing 3 times 1, then squaring it. We square 1, 1 times 1 is 1, times by 3 is 3. 2 squared is 4, 3 times by 4 is 12. Then we're going to have 3, if we square that we get 9, 3 times 9, 27. We're now going to square 4, 4 squared is 16, 3 times 16 is 48. And then we'll take 5, 5 squared is 25, 3 times 25 is 75. Now, what I'm going to do is take this out of my sequence. I'm going to take the quadratic part out of the original sequence. Now, if we go back to a previous example and we look at this one, if I take out the quadratic sequence, I'm left now with this linear of 4n plus 1. If I take out the quadratic sequence of this one, I'm left with a constant. So what we're going to do is remove now the quadratic part of this. So all I'm going to write in the next line is t, the term, minus 3n squared. So I'm removing the quadratic expression from this right here. So t minus 3n squared, 4 minus 3 is 1. If we get now 13 minus 12, that's 1. 28 minus 27, that's 1. 49 minus 48 is 1. 76 minus 75 is 1. Therefore, what we can see now is we've got a constant term. So once I've taken the quadratic out, I've got a constant term. All I now need to do to state the nth term of this is put it back together. We know that we've got this 3n squared, and then I can see I simply need to add 1 to each of the terms, and that will now give me the quadratic nth term. So I've considered now finding the second difference. I know the second difference is 6, therefore we've got 3n squared. I work out what 3n squared is, taking n to be 1, 2, 3, 4, 5 and so on, and subtract it from the term. That leaves me a fixed value. I know if I've got a fixed value, all I need to do is add or subtract that. So if this was minus 1, I take off minus 1. Now, how can we tell this works? Is this right? Well, let's sub some values in. If I take 1, 1 squared is 1, times by 3 is 3, plus 1 is 4. If I take 2, 2 squared is 4, 3 times 4 is 12, plus 1 is 13. If I take 3, 3 squared is 9, 3 times 9 is 27, plus 1 is 28. If I take 4, 4 squared, 16, 3 times 16 is 48, plus 1 is 49. So this now is the nth term for this particular sequence. Okay, let's try another one. So what we're going to do is put this in the table. Now, n, we will take n to be 1. That now is the number in the sequence. So this is the number of the term, and we're going to have 1, 2, 3, 4, 5. And the terms that we're given are 3, 9, 17, we're going to have 27 and 39. So if we now consider the first difference, so we can see that this first difference is not the same. Therefore, it's certainly not linear. So it's going up by 6, it's going up by 8, it's going up by 10, it's going up by 12. That is the first difference. So we know that it's not linear. Let's look at the second difference. What we're doing here is going up by 2. So it's 2, 2, 2. Therefore, the second difference is constant. We've got 2, so we can say that we're going to have an n squared term in our quadratic sequence. So what I'm going to do is now write n squared, and let's put this in. So what we'll do is take n squared. So n squared. Well, if I take 1, 1 squared is 1, 2 squared is 4, 3 squared is going to be 9, 4 squared is going to be 16, 5 squared is going to be 25. I now want to remove this from my sequence. What I'm looking for now is an squared, and that will be my quadratic bit, plus now bn plus c, and that is going to be either now just the constant of c or some linear nth term problem. So let's write in, now we can do this, let's do t minus n squared. So all t minus n squared means is I'm taking away the quadratic part of this sequence. 2, 5, 8, then we're going to have now on that one, that's going to leave me 11, and then we can have 14. At this stage, we should recognise this as a linear sequence. So if we consider this linear sequence, we can see now that it's got a common first difference of 3. Now, recognising this, I can simply jump in and say that this is going to be going up by 3. 3 times by 1 is 3. To get to 2, I need to subtract 1. So the linear part of this is going to be 3n minus 1. So if I consider now 3 times by 2, that's going to give me 6, minus 1 is 5. 3 times by 3 minus 1 is 8. 3 times 4 is 12, minus 1 is 11. So what I've got now is the quadratic part of n squared, and I've got the linear part now of 3n plus 1. So all we need to do is simply put this together, and we will have now n squared plus 3n minus 1. And that is the nth term of this quadratic sequence. So again, what I've done is look to find the common difference. The first common difference is not fixed, therefore it's not linear. I've gone to the second difference, that is fixed. It's 2. If it's 2, we've got n squared. If it's 4, we've got 2n squared. If it's 6, we've got 3n squared. I've then found what n squared is, taking n to be 1, 2, 3, 4, 5 and so on. I've then subtracted that away from the terms in the sequence. That's left me this right here, and I should now spot that this is simply a linear nth term problem. So if we were left with, in that row, minus 3, minus 3, minus 3, minus 3 and so on, what we could say is the quadratic nth term would be n squared minus 3. If I was left with, in this row now, for example, 4, and then we had now 4, 7, and then we had 10, we can see that this is going to be 3n plus 1. So that's what we're doing. We're looking now to subtract the quadratic part and simply express this now in two parts. We're bolting together a quadratic and a linear to give us now this nth term. Okay, so far we've looked at generating a sequence given the nth term, and we've looked at finding the nth term of a quadratic sequence. Let's now extend this slightly further and look at some questions that they may ask. One thing that they might ask is now find the 10th term. So if we write this out, and I'm just sort of thinking as I go, find the 10th term. Now you could probably continue this pattern in your head by simply adding now on here 2 more each time. So adding 14, adding 16 and so on. But what if I made that 100? What if I made it 1,000? What we need to do is now find the 10th term. So all we have to do for that, we can say from here, therefore n will be equal to 10. So let's sub that in. What we're going to have then is 10 squared plus now 3 lots of 10 and then minus 1. So that's going to give me 100 plus 30 minus 1, which is going to give me now 129. So we can say the 10th term is 129. So don't be tempted to do it manually, just simply sub in n is 10. What if we were asked if now one term was in this? Again, we could go hunting for it. Let's take a value. Let's say, is now the number 69 in the pattern? Now you could go hunting for that again, but let's actually look and use some of the knowledge that we might know. So let's see if that's going to be in there. Now if it's in there, what we can say then is n squared plus 3n minus 1 is equal to 69. If that's in there, if we sub some number in, it will give us 69. I subbed 10 in and I got 129 out. I subbed in now on here 1, I got 3 out. So let's see how we can deal with this. Well, that's a quadratic, and we can go ahead and write this in the form an squared plus bn plus c is equal to 0. We'll see if it factors, and then we can see now if we got solutions. Remember, if this is in the sequence, we're going to have integer solutions for n. So let's subtract it from both sides and set the right-hand side to 0. So n squared plus 3n minus 1 minus 69 is minus 70, and that will be equal to 0. Now it looks like I can factor that to n plus 10, and then we're going to have now n minus 7 is equal to 0. So this is telling me from the algebra that n is equal to minus 10, or now n is equal to 7. Well, let's consider n is equal to minus 10. We can't have minus 10 as n is a number. So quite clearly n is going to be 7. So we can say now that 69 is the 7th term. So let's just check if that would be the case. Let's go here. We've got the first 5 terms. So on the next one, I would add 14, which would be equal now to 53. And then the next time, I would add 16, which would give me 69. And we can see that's in there. But of course, if I ask you if 582 is in there, we don't want to be adding 18 and adding 20. So we want a method of where we can jump to find that term. So if we've got now positive integer solutions to this quadratic equation, then that term or that value will be in the sequence. So there we go, some basics on the nth term of a quadratic sequence, and hopefully that's helped you to get a head start. That certainly isn't the only way that you can do these problems. There are plenty of other methods that you could use, but this is certainly one that will see you through.